is the compressed liquid and the right side is the superheated vapor region, and in between it is basically saturated liquid and vapor region. So this diagram is a what kind of diagram? TV diagram, is it right? So it is the TV diagram. Similarly, we can draw the diagram for PV diagram. So these are the PVT surfaces. Like if you take the projection of this PV diagram and TV diagram and try to accumulate those projections, finally you will get a PVT surface. So hopefully if you see from this side, you will get the PV diagram, and if you see from top, you will see the TV diagram. So these are the two diagrams. So today we'll be solving some numericals and how to read the property table. For reading the property table, you just open the PDF and open the page number 8. So open the PDF and move to page number 8, 8 of 50. So in the PDF there are 50 pages. Go to the 8th page. Now this table is extremely important during solving numericals. So let's try to understand the meaning of each and every column of this table. So can you see this table in your laptop or mobile?
Yes, sir.
Okay, fine. So in the first class of the pure substance, I told you that if you go to that table, the table is written as saturated water temperature table. So if you read this line, it is written as saturated water. So what do you mean by saturated water? The saturated water means this. It is talking about the saturated water is basically talking about this line. So what is happening in between this and this? So this is the saturated liquid and this is the saturated vapor. So in between, every state can be termed as saturated water state. So what is saturated water? Saturated water is basically the combination of saturated liquid plus some part of saturated vapor. Okay, so I told you what this instant explains. If you go to this instant explains that if you have a water and that water, if this pressure is atmospheric pressure, you can tell that at this point the pressure is constant and the temperature is constant. If you heat further, what will happen? The pressure and temperature will remain constant, but gradually the water is going to convert into vapor. So at this point, if you check this point, at this point there is no vapor. But if you add a delta amount of heat, the vaporization will start. If you go along to this line, what will happen? That gradually the percentage of vapor is going to increase, and finally the whole liquid is going to convert into saturated vapor at this point. So this whole line can be termed as saturated water. So if you look into the table, what is happening in the table? If you see there, in the saturated water table, in the first column, they have mentioned about a temperature. So if you see this is a temperature table. So this is temperature. So if I see the temperature is 0.01 degrees Celsius, 5 degrees Celsius, 10 degrees Celsius, 15 degrees Celsius, and what is in the right side? Can you tell me what is the right side, second column? What is the meaning of second column? What is the meaning of second column?
Saturated liquid form.
So yeah, exactly. So I told you that whenever there is a boiling, if you fix the temperature, the pressure will get automatically fixed, or vice versa. If you fix the pressure, the temperature directly got fixed, because they are not two independent parameters. Like whenever you say my water is boiling at 100 degrees Celsius, this directly ensures that the pressure must be 1 bar. Do you get my point? So the pressure may be 1 atmospheric pressure. So whenever you are fixing a temperature, if it is a phase change process, the pressure is already getting fixed. And we already know that. I told you about the pressure cooker example, that whenever you are increasing the pressure, your boiling point is increasing. So the same thing what we have discussed in the previous class. So you can verify that if you see the table. I don't know it is visible or not. If you see, this is the temperature at 100 degree temperature, 100 degree Celsius temperature, it is showing the pressure is 101.42 kPa. So kilopascal. So if we multiply with by 10 to the power 3, so finally it will become some 101 into 10 to the power 3. So it is equivalent to 1 bar. Not exactly 1 bar, you can say it is equivalent to exactly 1 atm pressure. So this 101.42 kPa correspond to 100 degree Celsius pressure. So whenever you are switch on your pressure cooker or something like that, what is going to happen? Your saturation temperature is going to increase. Why it is going to happen? Because you are increasing the pressure. So maybe at 2 bar pressure, your boiling temperature is 125 degrees Celsius. That's why you are getting early cooking, because of this high elevated temperature that is causing easier to boil something. So by the first two column, I can easily determine that what is my saturation temperature, and at that saturation temperature, what is my corresponding saturation pressure. You got my point? So if I tell you that at 150 degrees Celsius, what is the saturation pressure? Can you find out? At 150 degrees Celsius, what is the saturation pressure?
476.16 kilopascal.
Very good. So you can tell that to increase the 50 degree, to increase 50 degree boiling point, or maybe you can tell that if I try to solve one simple numerical. Suppose if you want to increase your boiling point 50%, suppose you are at 1 atmospheric pressure and you are willing to increase your boiling point 50 degree, how much pressure needs to be increased? What is the change of percentage of pressure for that? Can you solve this numerical quickly? I want to increase my boiling point 50 degree at 1 atmospheric pressure. How much percentage of pressure needs to be increased? Can you tell me?
376%.
Percent?
Yes, 100 plus 376 equal to 476.
Yeah, it is basically 476 by minus 101.42 divided by 101.42. So it is around 350%, 370%. Is that right?
Yes, sir.
Yes,
It is
Yes, sir. 370%.
So it is
coming
coming
369.49.
369.49.
Yeah. So basically, you can tell me in the form of times. So the pressure, if you want to if you want to increase the saturation temperature 3/2 times, your pressure needs to be multiplied with something like 3.7 times. Is that true?
Yes, sir.
Yes, sir.
Can we tell that? Yes.
No, sir. It's need to be linear for all temperature. I mean, it's true for 100 degrees Celsius, not for 150.
No, my question is that suppose I am boiling at something at 100 degrees Celsius. My saturation pressure is this one, 101.42. If I want to boil at 150 degrees Celsius, how much I have to increase my pressure. So this is the difference of these two, 476.16 minus 101.42. So this is I'm trying to explain. So basically what I'm trying to say, that these two columns are interlinked. Each column is representing the saturation temperature corresponding to that saturation pressure. So I told you in the beginning that this is the temperature table. So if you go further, if you go to the next page, this is also the temperature table. If you go further, you see at the page number 10, it is written as saturated water pressure table, where you can see that they have mentioned the pressure in the first column. Corresponding temperature is mentioned in the second column. Here also you can see whenever your pressure is 101.325 kPa, corresponding to that your boiling point is 99.97. Can you see that?
Yes, sir.
Yes, sir. So if you see at 500 degree, at 500 kPa pressure, if it is 500 kPa, at 500 kPa, your corresponding boiling point is 151. Can you see that? At 500 degrees Celsius, your pressure is 151.83 degrees Celsius. So basically I'm trying to say that these two tables are same. The pressure table and the temperature table, they are both same, but only in the pressure table, the pressure is gradually varied with equal interval, and in the second table, they have independently varied the temperature, corresponding the pressure is given there. So these two tables, we have understood the first two column of these two table. Is that right? Do you have any doubt from the first two column? Do you have any doubt from the first two column?
Sir, in both the table, sir, can you hear me?
Yeah, perfectly.
Sir, in both the table, the saturation temperature is maximum, showing that 373.95 degrees centigrade.
Exactly.
What is the specialty in this case?
Yeah, that is the temperature of the critical point. I told you in the first class that in the first class of this phase change, that there is one temperature that is basically called the critical point. After that, there is no phase change. Can you recollect this?
Yes, sir.
If I show you, if you look into this point, good question. So if you look into this point, this is the 373. So above this point, there is no kind of phase change. Before that, there is a phase change process. Okay, so whatever boiling point they have mentioned, this is the last temperature. Up to that, you can achieve boiling. If you go more than that, you will never see boiling for water. Okay.
Okay, sir.
So, good question. So, this is the first two column we have understood. Okay, fine. Let's see what is there remaining. So, if I go to the slide, what they are trying to say that let's try to see one example problem. So if I try to see what are the other columns, you will see that one column, if you see the third column, it is written as saturated liquid. What is this small VF? What is the meaning of this small VF?
Specific volume of the saturated liquid.
Very good. Saturated vapor. So this is VG, specific volume of the saturated vapor. Here they have written what? That the saturated liquid UF. UF is the specific internal energy. The saturated vapor UG. This is what? The saturated, it is basically the specific internal energy of the saturated vapor. And in between, there is written as UFG. UFG is nothing but the difference between UG minus UF. So I will explain it later. Similarly, there is saturated liquid having some specific enthalpy HF, the saturated vapor which is also having a specific enthalpy Hg. The difference of these two enthalpy is written as HFG. Similarly, for the entropy, what is entropy I will tell you later, but at this point of time you can consider that this is also kind of a property. So what is happening there? It is written as SF, specific entropy at saturated liquid and specific enthalpy at saturated vapor. Corresponding to that you have saturated SFG, so which is basically Sg minus SF. So if I show you the PPT, if you see the table, that what is written there, this is the table. So the saturation temperature we understood, the saturation pressure we understood. Now there is written that the UFG, if you see UFG, this is UG minus UF, HFG, Hg minus HF, and SFG is Sg minus SF. What is the meaning of this? Just you consider this is nothing but algebra. Some final value, the gas, saturated gas value minus the liquid value. So what I'm trying to say that this F, meaning F, if you understood F, this is F and this is G. So any state on this line is basically designated by F, and any line, any point on this line is designated as G. So what I'm trying to say, what is the meaning of the table? The table tells that what is your temperature, corresponding to that what is your pressure, second column. Then it tells you what is your specific volume of the liquid, this is VF, and this is VG, this is UG, UF. The the internal energy of this point is UF. Here simultaneously I have UG. Here I have HF. Similarly, I have also one Hg. Here I have SF. Here I have Sg. Is that right? So for every temperature, every phase change temperature, if I try to summarize it, for every phase change temperature, there will be a phase change pressure. There will be a saturated liquid state. For that saturated liquid state, you have a specific volume at that saturated liquid, the internal energy of that saturated liquid, the specific enthalpy of that saturated liquid, and the specific entropy of that saturated liquid. Simultaneously, you have a internal energy of the saturated vapor, the internal energy of the saturated the specific volume of the saturated vapor. So at the state G, you have specific volume of saturated vapor, internal energy of the saturated vapor, specific enthalpy of the saturated vapor, and specific entropy of the saturated vapor. So for each temperature, you have these datas. Similar to, for each pressure, you have a corresponding saturated temperature corresponding all these values. Do you understand? Now if you look into the table, discard. So now if we look into the table again, if I zoom it, so see, I have a temperature corresponding to that temperature I have a saturated pressure, corresponding to that temperature and pressure I have a liquid volume and a vapor volume. I have a liquid internal energy and a saturated vapor internal energy. I have a saturated liquid enthalpy. I have a saturated vapor enthalpy. I have saturated liquid entropy and saturated vapor entropy. Is that okay up to this much? Is it okay? Any doubt up to this much?
Sir, I have a doubt.
Yeah.
The internal energy of the saturated liquid is increasing more rapidly than that of the saturated vapor, and increase in the actually the saturated vapor internal energy of the saturated vapor is starting to decrease after a certain point. Why is this happening?
Which point you are trying to say? No. Is it right that?
Yes, sir. After certain point, the internal energy of the saturated vapor is starting to decrease.
Okay. So yeah. So as you are reaching, what is going to happen? As you are reaching to the final pressure, you can see that what is happening. The internal energy is continuously, the liquid state internal energy is increasing, and the vapor state that is also decreasing, and finally the gap between these two is finally reaching to zero. Can you see that?
Yes, sir.
So this is happening. This is, I told you in the previous class that these are the properties that are basically observed properties. So what is the physics behind these values? That is basically a part of statistical thermodynamics. We are never going to discuss how we are obtaining these values. Finally, we are going to use this value for our calculation. But in a way, you can understand it something like this. As you are basically, what is happening now, I can tell you some like a hint of this. As you are increasing your pressure, your saturation temperature increases. If your pressure increases, according to that, your internal energy is also a function of that. Your internal energy is also increasing. Now, as your internal energy is increasing, you need to supply less energy to convert it into a vapor state. So that is why the vapor state has a lower energy as you are moving in the higher pressure. I don't know, I'm trying to say that if I give you one example, like suppose you are at this temperature. This is your temperature. This is your temperature 205 degrees Celsius. This is the gap. This much amount of energy you need to supply to convert into vapor. Now, as you are increasing your pressure and temperature, the internal energy of the liquid state is gradually increasing. Now, finally, you need less energy to convert into vapor. You can see that UFG, that is basically the difference between the state, that is also continuously decreasing. That is why the final value of UG, that is also decreasing. So this is one observation. I don't know, I have correctly explained you the thing, but I am trying to see that these are the observed phenomena that we have found from the experiment. But what is the proper molecular explanation of this? I think this is out of the scope of this coursework. So I think we should not look into those phenomenological change, but more into those values and these calculations. So, are you satisfied, or I don't know? Somewhat I have explained the point.
Yes, sir.
Okay, I don't know, but still I understood your doubt. But in thermodynamics, in engineering thermodynamics, we don't explain these things in the form of statistical physics. So I really, if I say truly that it is very difficult to answer these questions in this following way, but somehow we can understood in another phenomena that as you are increasing the temperature, it is now the liquid state. Now for the liquid state, it is easier to convert into vapor. So as you are increasing temperature, what is happening? The molecular energy of those liquid molecules, it is simultaneously increasing. Now it needs lesser energy to convert into vapor. That is why the vapor state internal energy is continuously reducing as you are increasing the temperature. Somewhat you, by this way you can understood, but if you have still doubt, we can I can further explain it later. So if I try to continue from this point, so now if you
Sir,
see the HF, yeah.
Sir, can we explain this in this manner that when the temperature, saturation temperature increases, in the upper direction, the vapor dome also shrinks towards the critical point, and at the critical point, the liquid and vapor, they actually coincides with each other. That's why the UFG becomes 0, because UF and UG are practically same at that point.
Yeah, I understood your point, but I am trying to say which one is the cause and which one is the effect. The graph is the effect or the graph is the cause. So you are trying to explain the thing in a form of a graph, but how we got this graph? When she is trying to ask me that, sir, how you got this graph? I am trying to say that these values are obtained from experiment, and if you want to explain why it is happening, you have to go to molecular physics. So that is why whatever you are saying is perfect, that I have a graph, as I am moving in the upward direction, the curve is converging, so the gap between these 2 points are reducing, so you can tell me that finally the difference is reducing. But what maybe she is asking, that why this graph is converging, why this graph is not expanding?
Yes, sir.
You
I was asking that. What is the actually physical reason behind that?
Yeah, the physical reason I told you, that properly if you want to explain, you have to go to the molecular physics. Other way you can understand it like this, that suppose your water is at 100 degrees Celsius temperature. If you heat it, if you change the pressure, it will go to suppose 200 degrees Celsius. Now at 200 degrees Celsius, it is easier to convert into vapor than 100 degrees Celsius. If your liquid as 100 degrees Celsius temperature and suppose 1 bar pressure, you have to supply lot of energy to convert into 100 degrees Celsius vapor. But suppose you are staying at 200 degrees Celsius, you need lesser energy to convert into 200 degrees Celsius vapor. So that is the point I'm trying to mention you, that as you are elevating your saturation temperature, you need less amount of energy to convert into vapor. That is why the difference between these two lines is continuously converging. So this is the way you can physically understood. But if you want to know the perfect reason behind this, for that, I again repeating that for that you have to go to molecular and statistical physics, and really I have no exposure of that thing in an undergraduate course. So I don't know, I'm skipping the answer or not, but somewhat I thought that I understood your question, and partially I have answered your question. So shall I proceed? Shall I proceed? Yeah.
Yes, sir.
Okay. So so basically we understood the meaning of each and every column. Everyone understood the meaning of each and every column? Everyone understood meaning of each and every column? You can open this page, the page number 850. So you can simply open the page number 8 and 50 and just check the table. Okay, so now the question is that why we need this table. The reason behind this, if I go to the presentation, suppose I want to solve one problem. Let's see one problem. So consider this question. A rigid tank contains 50 kg of saturated liquid water at 90 degrees Celsius. Determine the pressure in the tank and the volume of the tank. Can we determine this? What will be the pressure? Is it more than atmospheric or less than atmospheric? A rigid tank contains 50 kg of saturated liquid water at 90 degrees Celsius. So it is trying to say that
Less than 1
Less
atmosphere.
than
less than
atmosphere.
what atmosphere exactly. So because they have mentioned that it is saturated, that means it is about to boil. So that means it already reached to the boiling point. So we know that at 1 atmosphere pressure, it cannot reach to boiling point. It will be 10 degrees lesser than the boiling point. So it is already reached to the boiling point at 90 degrees Celsius. So what will be its pressure? It will be the pressure corresponding to 90 degrees Celsius saturation temperature. So if I check the table, if I go to the table, I will look into the temperature table because the temperature is mentioned. So if I go to following 50, 50, 60, 70. So if we go to 70, is it the pressure table or the temperature table? Temperature table. So if I go to the 90 degrees Celsius, you see what is the pressure? What is the pressure? What is the saturation pressure at 90 degrees Celsius?
70.183
183? Yeah, exactly. So here it is written that the pressure is this. Now the question is that what is the volume of the tank? So calculate the volume of the tank. You know the mass. So if we multiply with the specific volume, I will find out what is the final volume. So to calculate the specific volume, I have to find out that V, the specific volume, equal to VF at the rate 90 degrees Celsius. Is that true? Okay. So VF at the rate 90 degrees Celsius is equal to, let's go back to the table. So if I am there, the VF, this is the VF, the third column. If I go down 90 degree, it will give me this volume. Is that right? 0.001036. So if I know the volume, if I simply multiply it with the mass, I will get what is my final volume. This is the volume of the tank. Just you try to understand that these things are not new to you. Like suppose just consider one example, that just consider one example. Suppose you have a small tank which is filled with water. What will happen? If we slowly heat that tank, the water is going to expand. Is that right? Because of thermal expansion. Similarly, suppose someone told you that you have water at 10 bar pressure. Suppose just tell me one question, that what is the mass of your 1 liter bottle, filled water bottle? What is the mass of your 1 liter filled water bottle?
1 kg.
1
Around
kg.
1 kg.
Around 1 kg. Can you calculate that using this table? Can we calculate this using exactly this table? Can anyone try this and tell me, explain me? This was an information, but if I ask you that what is the exact mass?
Sir, we have to know the temperature of the water,
Okay.
then
So now tell me that what
dividing by
is,
the specific
yeah.
volume.
Yeah, fine. So now tell me what is the exact weight of 100 degrees Celsius liquid water at 1 atmosphere. Can you tell me? You have one bottle the volume is 1 liter. Now the bottle is filled with 100 degrees Celsius water. If you press this, if you take this bottle just over a just like a mass measuring machine, those measuring thing, and put hot water over it, what will be its mass? More than 1 kg, less than 1 kg?
1.5 more than.
Hello?
It would be less than 1 kg.
Noise is coming. Someone is talking, but the speaker is not properly working. Now I'm
Around
Sir, it would be
0.
less.
1.043
kg.
kg.
Yes.
So it is more than 1 kg.
Sir, I think it
Am I
would be
audible?
0.958 kg.
Okay, so we already got 2 answers. So I just note down. Yeah. Tell me, the first option was 1 point.
So
I will
1.043.
1.343.
043.
043. Okay,
Zero.
first option. We got first option. Next, 9 point 0.9. What was the next option?
0.958 kg.
958
Yes, sir.
kg. Let's see which answer.
0.958 kg.
Yes, sir. Yes, sir. 0.958. 1 by 1.043.
Yes,
Yeah,
sir.
exactly. So
Density
you
equals to
already
1
know
by specific volume.
specific volume. Perfect. Perfect. So you understood it perfectly. You have understood it.
Less than
This is the way. This is the way. So so what is the interpretation of this? If someone is giving you, if someone is taking one bucket and gives you hot water, you should not take it because it is less weight. So you always look for cold water. Otherwise, he will give you 0.95 kg in place of 1 kg. Okay, so this is the way we can use the table. So let's try to see another example. If you see this example, a piston cylinder device contains 0.06 meter cube of saturated water vapor. So the first point is important, that it contains 0.06 meter cube saturated water vapor. So it is basically on the right side of the line at 350 kPa pressure. Determine the temperature and the mass of the vapor inside the cylinder. So I know that it is basically saturated vapor. So if I know it is a saturated vapor and know the temperature, can we find out the saturation temperature? So let's go back to the pressure table. Now I have to look the pressure table. Initially I am looking the temperature table. So I will go to the pressure table. So this is the pressure table. This is the temperature table. So I have to go to the page number 10. What was the pressure? 350 kPa. So here it is my 350 kPa, and 350 kPa is the pressure, and this corresponds to 141.30 degrees Celsius. Is that right? So I know what is my temperature. Next, then they are asking that you know the final volume, and you know the final volume, and you have to calculate what is the mass of the vapor inside the cylinder. So if you know the final volume and if you know the specific volume, if you divide the final volume divided by the specific volume, so if I know the specific volume from the table, how I can find this? Can you verify this data is true? Can you verify the table?
Yes,
Is
sir.
it coming properly or it is mistake? There might be mistake. Can you check? Is it coming?
Yes,
Okay,
sir, it's
fine.
correct.
So if I know the final volume and it is the G, why it is G? Because it is written as saturated water vapor. Okay. So if they ask me to find out what is the mass, I will simply divide this total volume with the specific volume. So this is nothing but what? V into rho, because already someone told me that 1 by specific volume is nothing but the density. So rho into volume equal to mass. So I will get my mass. Any doubt up to this much? Is it getting difficult? Shall I repeat any part? Shall I move on?
Yes, sir.
আর কারো কোনো জায়গা বুঝতে অসুবিধা হচ্ছে? আমি তাহলে আরেকবার এক্সপ্লেন করব। কারো যদি কোনো জায়গা বুঝতে অসুবিধা হয়, you can ask me. Any query that comes to your mind? Okay, so if we see this diagram, if we see this diagram, this is the point at the right side, and this corresponding to Vg. Okay. Now, next problem. A mass of 200 grams saturated liquid is completely vaporized at constant pressure of 100 kPa. Determine the volume change and the, just wait for 1 minute. Can you solve this problem? A mass of 200 gram saturated liquid water is completely converted into vapor at constant pressure 100 kPa. Determine the volume change and the amount of energy transferred. So you are at this point. This point corresponds to 100 kPa and liquid, and the mass is 200. And this point corresponds to 100 kPa, but completely saturated vapor. But the mass remains same. They have asked two questions, that what is the volume change? What is the volume change due to the phase change? And what is the amount of energy that is needed to be supplied to support this conversion? Or
Sir.
how much energy is required to convert into completely vapor? Can we solve this?
At 100 kilopascal pressure, the specific volume of the liquid, means liquid water, and the specific volume of the gas, we will check it and multiply it with 200 gram to get the volume of both the state. Means the gas state and as vapor state as well as the liquid state, and then just subtract it, so we can get the volume change.
And energy?
And from that line we can get the energy. If
With value?
Sir, enthalpy.
For energy, we can use the difference between internal energy of the gas state and the liquid state, and that is given in specific form. So we have to multiply the mass with it.
Okay, now Yeah, I got your point, but my question is that is it the internal energy or the
No, sir, enthalpy.
enthalpy?
Enthalpy, sir.
So how to say that? How you know that it is the enthalpy? This is not.
Sir, here the pressure is constant, and we know that enthalpy is defined as the heat supplied at constant pressure. So
Very
we
good.
can tell that.
Very good. So what you are saying that if it is a constant volume process, in that case it will be the difference of enthalpies. But as it is a constant pressure process, it will be the difference of enthalpies. If it is the difference of, if it is a constant volume process, it will be the difference of internal energy, U.
Yes.
I made a mistake, sorry. If it is the difference of internal energy, that means the process is constant volume.
Constant volume.
And if the process is constant pressure, it will be the difference of enthalpies. So can you calculate and tell me the answer? So we can verify it. Just simply open the table, just take a pen and pencil and calculate and tell me. If you are sleeping in your bed and watching it, just please get up and take a pencil and pen and do a one-line calculation, please. Even you can use your mobile calculator. Please get up and do. Otherwise, you have to put individual effort to learn this. At this point of time, we can learn simultaneously during the class. Otherwise, you have to learn it, but in that case, you have to put your own effort. So if you are still watching, just simply get up and just take a pen and pencil and calculate and tell me the answer. It will take simply 5 minutes.
Sir, 451.28 kilojoule, the energy change.
Kilojoule. Okay.
Yes, sir.
And what is the change of volume?
0.386.
Is it coming?
0.338 meter cube.
Okay. And what about the energy transfer?
451.28 kilojoule.
451.5 kilojoule.
Okay, so this is a difference of fraction. So let's see. So let's verify the answer. Open the Cardan and see. Yeah, is it coming? So what they are trying to say, that you have calculated Hg, then you subtracted with Hf, but they already included one parameter, which is Hfg. So it is already subtracted. So you can use this value for your calculation. Whenever they are talking about phase change, the Hfg, the Hfg is nothing but Hg minus Hf. So you can use this thing, and from that you can calculate. But life is not so easy. Here till now, whatever we calculated, we have only focused what is happening on this line and what is happening this line. But we are never bothered that what happened inside this. So what is the property here? If you consider one part, at this point, there is some part is saturated liquid and the some part is saturated vapor. So it is nothing but a mixture. If you consider a container, in that container, some part is filled with liquid and some part is filled with vapor. So how to calculate the property of these mixtures? So that is the part of the next job. So just I'm giving one example. Suppose you have one mixture and in that mixture some part of the liquid is converted into vapor. So there will be some part which is saturated liquid and there will be the remaining part is saturated vapor. So I am defining one parameter. That parameter is called X. Please follow, this part is little bit complicated, so please pay attention. So this part is called as X. X is defined as a quality. What is quality? Quality is nothing but the mass of the saturated vapor by the total mass. But this is valid only during phase change. If there is a phase change, whenever there is a phase change, then only this is valid. So what is that? That X equal to the mass of the saturated vapor divided by the total mass. So this is nothing but what? The mg. Mg is the mass of the saturated vapor, and mf and plus mg. You can consider F means fluid. F means fluid and G for gas. Okay. So this is will be something easier for you. Whenever you talk about G, G means saturated vapor. Whenever you talk about saturated liquid, so it will be fluid, so it will be SF. So whenever you have a mixture, that mixture can be averaged as a uniform substance. As it is a homogeneous, I told you, is a pure substance. So as it is a pure substance, you can consider this whole thing as a saturated liquid vapor mixture. You can consider there is some liquid, there is some vapor, but there is one kind of a spoon and someone is mixing this liquid and vapor simultaneously so that it can create a uniform mixture. So now we are trying to define the property values for intermediate points. Just like you try to consider the previous example. Like if someone told me that if I am starting this process, if I am starting this process at the point 1 and the process ends at point 2, but it may not happen, that process may not end at point 2. It may happen the 75% of the liquid can be converted into vapor. If 75% liquid is converted into vapor, what will be its final volume? What will be the value of the energy that will be required to supply to support this phase change? It may happen. We never always deal with the end points. There are some situations we have to also deal with the intermediate points. To determine the location of the intermediate point, I am defining a new parameter. That new parameter is called the X. X is called the quality. So now tell me one answer, that if you are lying on the saturated vapor line, what is the value of your X?
1.
If you are lying at the saturated liquid line, what is the value of your X?
0.
Very
Zero.
good. Fine. So you understood. Okay.
0.
Yeah. So basically we understood that the value of X will vary from 0 to 1. Okay. Now let's see. So what I can do, that the total volume, if this is my total volume, this total volume can be written as Vf plus Vg. This V means some intermediate mixture. It relates to some mixture. I am using my mouse to write it. I am developing some extraordinary skills. So let's see that this is Vf and this is Vg. So the total volume can be written as Vf plus Vg. Similarly, the mass can be written as Mf plus Mg. And this is the average volume. This is the average volume that you need to determine. What do you mean by average? Whenever you mixed it, whenever you have uniformly mixed it. So you can write that my total mass into that average specific volume is nothing but my liquid volume into the liquid specific volume, the liquid mass into the liquid, the saturated vapor mass into the saturated vapor volume. So this is total. this is total. Total into the average is equal to individual into the individual plus the individual into the individual. So here I can represent this like this. So my average property can be written as this. So now if I implement this, my x equal to mg by m equal to mg by mf plus mg. So I can write down that my mf by m is nothing but 1 minus x. So this expression can be written as my average volume equal to mf by m. This part can be replaced as 1 minus x into vf plus the remaining part mg by m. This can be written as x. So any average property can be written as summation of the liquid state and the summation of the vapor state with some quality factor. So what I'm trying to say, that if you put x equal to 1 in this equation, what will happen?
Just Vg.
Is it the saturated vapor?
Yes.
We know that x equal to 1, everything became saturated vapor. What is the value of V at x equal to 0?
Vf, that means saturated liquid.
Only
Fine.
VF.
So is it going with our understanding? Is that right? So
Yes.
any intermediate point can be written like this. Any intermediate point. You have to simply put the value of x. What is x? How much fraction of vapor converted, or how much mass of vapor is existing divided by the total mass. So if you have completely converted the total mass, it will be total mass divided by total mass, it will be 1. If you have not yet started your boiling, so there is no vapor, so x will be 0. So any intermediate property can be determined the value of the x. The value of the x will determine what will be the average value at intermediate points. So let's try to solve one problem. So let's assume one problem. Just wait for 1 second. Now look into the problem. So a rigid tank contains 10 kg of water at 90 degrees Celsius. The previous problem, but here they are referring it is water. What is the state of the water that not yet mentioned? It is simply written as water. There's 8 kg of the water is in the liquid form and the rest is in the vapor form. Determine the pressure of the tank and the volume of the tank. Can we solve this problem? So you have, if you look into this diagram, you have a 10 kg mass, this 10 kg mass, you have remaining water at 8 kg, and the other part 2 kg of the water is converted into vapor. Now they are telling you that what is the total volume of this tank. How to solve this problem? What is the value of x here?
1 by 5.
1 by 5. Okay, fine. So basically 0.2. What will be
Yes.
the pressure?
At 90
Pressure will
degrees
get affected
centigrade.
by x.
70.18.
Pressure will get.
So 70.18.
So there is no importance of pressure in x. Is that right? Because temperature determines pressure. Okay. So throughout x equal to 0 to throughout x equal to 1, your pressure will remain always same. Your temperature will remain same. your pressure will also remain same. Okay, now can we find out the final volume of the tank? Will you try, please? Anyone?
It's 4.726 27
4 point
727
unit.
meter cube.
Okay, any other answer?
Sir, 0.473 meter cube.
You have calculated for the mass? Have you checked the mass?
Sir, the formula is 1 minus x VF.
That is the specific volume, but they are looking for the volume of the tank.
Okay. Okay.
So that is happening for 1 kg.
স্যার আমার
Yeah,
একটা
exactly.
3.77 আসছে মিটার কিউব
3.77 আসছে. Okay, so now tell me, what was your pressure? Saturation pressure?
70.183 kilopascal.
Very good. So now what is your x? 0.2. Now at 90 degrees Celsius, what is your VF?
0.001036 meter cube
So
per
what
kg.
is your VG?
2.3593
Okay,
meter
so
cube per
if
kg.
they are correct, then if you see the calculation, so it is VG plus VF. So if it is your VG, you know the value of VG, you know the value of VF. So you multiply it with the mass, you will get the final volume, 4.73 meter cube. Or even you can calculate in other way, just like calculate the x. You know x V equal to VF plus x into VFG. Is that true? Is that true?
Yes, sir.
How we can write it?
So V equals to 1 minus x into VF plus x into VG. So this is VF plus, if we take the x as common, then in the bracket it will be VG minus VF. So VG minus VF is VFG. So we can write this.
So is that right? So I can write it VF plus, as you told me, take x common, it will be VG minus VF. So finally I can write down it is VF plus x into VFG. That is why they have given you some FG values, but for volume it was not given. But finally in this way we can calculate the average specific volume. This is for the mixture. This is for the mixture. Now you can, if I multiply with the total mass, I will get the volume. I can use it like this, or even I can solve it like this way. I know the total volume. I know the total volume, and if I simply multiply it with the mass and the corresponding liquid volume, multiply with the mass of the gas into multiply with the vapor volume, I can find out the total volume. So this is the way I can find out anything what is happening in between. So you see, this is what? This is 0.2. This much thing that you have converted into vapor, and this much is still liquid. Okay. So this is the way you can use the tables and solve the problem. So let's solve another problem, little bit challenging problem. This is the problem from your assignments. So if I go to the assignments, can you solve the first problem? Please read out the question. Please read out the question. Anyone? The last problem of the class. Please participate.
Sir, at 105 degree C, the saturation pressure is 120.90 kilopascal. 120.90 kilopascal, but P atmosphere is that.
Just tell me the answer. Tell me the final answer. If you can solve this problem, you are really smart. What is the weight of the lid or the cover of your boiling bowl? What is the weight of your cover of the pot? Can we boil water at 105 degrees Celsius? No. At 180 atm pressure? No. So there must be some additional
Sir,
pressure.
will be the answer 281.527 something like that.
Sir, 5.27 into 10 to the power minus 4 kg. I think.
Minus 4 kg.
Sir, would it be
Total pressure is
35.85 kg?
120.9 and is equal to, it will be 101 kilopascal plus the weight by area.
Very good.
So sir,
mg by a. mg by a.
Yes,
You
sir,
know
A
the
is
m.
equal to pi d square by 4. So
Pi d square by 4. Perfect. It is
okay,
in
sir,
centimeter.
10 to the power minus 4 আর ওদিকে কিলো পাস্কাল আছে তাহলে 10 কিউব গুণ হবে সো স্যার 0.527 is coming kg.
Is it true? Verify. Please verify other. So you have one equation. What is that equation? The equation is that corresponding to 105 saturation pressure, it is somewhat maybe what is the pressure? 129.
Sir, the answer may be 35.85 kg.
35 kg cover. It
I
will be
think
too much. Okay. Let's see. So I am just forwarding this assignment. If you have time today. There are several interesting problems. Maybe there are only 11 problems, 12 problems. It is based on the previous two chapters. One is from your one is from your steady state energy equation, and other one is from your pure substance. So read these two chapters and try to solve these problems. Okay, so this much is for today.